Hello viewers, welcome to the Semiconductor webinar. You are already familiar with Bhavesh and Jayashree. They have already presented a very exciting journey in our last episode of TSW. Today they are back with another exciting topic they are going to present in today's episode. Cutting short the introduction part, I'll move to Jayashree and Bhavesh. So over to you, Bhavesh and Jayashree.
Hello everyone, welcome to our semiconductor packaging and testing session. So we will start with the basics of packaging, how is the fabricated devices impact to the later steps, and we will continue over it. Myself Padwani Jayashree, and you already know Bhavesh. So we will start our session by now. Uh, like what are you expecting would be almost covered in this session. Let's move to the next slide. That's what are the contents of this today's session. So we will going from basic flow, like how the wafer what is wafer firstly. So we have fabricated our wafer, device has been fabricated, and now we have to package it so that it doesn't get harmed or damaged due to the environmental stress or some kind of eventually the humidity, pressure, temperature doesn't affect the device. So that's the necessary of the packaging, and we are going to learn the each of the multiple steps which are being covered with the fabric after the fabrication for the packaging flow. So firstly we will start with the what is the packaging flow, and then different types of packaging, and then last to the testing purpose. Okay, so let's begin with the roadmap. Then firstly we are going to see that what is the complete flow. As this you can see in this image itself, this is a complete wafer. So what is wafer, and what is a single chip die? So in this image, think of it a wafer, and a wafer is having multiple number of devices, and then devices are individually cutted off and then getting into a die. So yes, a device which is being individually, then it is called as a die, and then die is being packaged so that it get a complete device. That's called a package. These are the three individual terms: a wafer, a die, and a package. So, and in the left right hand side you can see how this stacking has been done to create a stack, and there we can see the layers of the packaging, like from base to the uppermost layer. And these are all the terms which would be learning in this next session, I mean continue session. Let's start with this individual steps. So firstly wafer, and then wafer sawing methods. So what is wafer sawing methods? Basically wafer sawing is how to cut the wafer into individual dies, and then the die attach. So what is the die attach? Die attach is, think of a gum and a paper or a stick or a glue gun, and then sticking in onto something. So that is die attach. Then what is wire bonding? So basically wire bonding is connecting the base layer and that device internally, so that for the electrical connections and the thermal conductivity. Then molding, basically molding is encapsulation. Like as we know into the computer languages also, C and Python language, encapsulation. So yes, encapsulation is same as we are covering up something so that it doesn't get harmed. In this we are protecting from the environment. And then marking. So what is basically marking? Marking is actually a kind of, we can say, like naming, giving, providing names of the individual companies, or who created this, by which logo and everything is in being marking. And then plating. So basically what is plating? The plating word itself is actually defining, like we are going to enhance the surface conductivity and to provide from the corrosions, specifically like when it get to context with the another materials into the surrounding, it doesn't get affected. So yes, we are doing plating. Trimming and singulation process, there are two types of wafer sawing. Once if we are going for the wafer level packaging, then there is different types of process. If we are going for device level packaging, then there is a different. So depending upon the requirement and upcomings, we are going to do different types of processes. And then the final test. Yes, final test is basically very required, because to check the device or the chip is actually correct, giving the good amount of yield, or it is not actually giving performance based, then to check its electrical testing, then thermal testing, mechanical testing, environmental testing. There are multiple types of testing which we are going to see in this individual steps. Now let's start with the firstly, what is wafer saw? Okay, so there is a next slide where we can see that firstly we will go for the what are the different types of packaging. Okay, so let's start with the what are the different types of packaging. As this, you can see there are multiple divisions of the types of packaging. It would be getting confused. So let's go individually step by step. Basically, what is it? I mean, why are we doing the packaging? So depending upon the size constraint, input output connections, then thermal and electrical performance, cost, and yes, the most important is and applications. Basically, what is and application? So think of as if it is a mobile or automotive, then the chip eventually chip will require different types of packaging also. So we are going to learn about the different types of packaging. So as this you can see in this image, there is the word written DIP, dual inline packaging. So basically what it is, so it is through hole packaging within the two side of the leads, and basically it's used in commonly in microelectronics or analog ICs. Yes, it is easy to solder, but yes, it's kind of bulky. And then QFP, quadra flat package. You can see in this images also. You can just think of it, and we will later learn individually. But yes, for now you can just think these words and what are basically why we are using and where we are using this kind of packaging. So QFP, quadra flat packaging. So basically, is surface and a mount packaging with the on the lead frame on the four side. And yes, it is also used in microelectronics and embedded processors. Actually, it is good for the input medium for the input output density. It can be used, and depending upon the cost also, we will think about it where to use and where not to use. Then BGA, ball grid array. So basically, it's like a array of solder balls on the bottom, and then we are putting upon the device over it. Yes, it is good for excellent for the thermal and electrical performance, where we are supposed to maintain this conditions, and then it is basically used in CPUs and GPUs. And then CSP. So CSP is small types chip size chip scale package. So this is the smallest type of die packaging, because it is, and yes, this is the most important, as we all know that in which in the computers and if mobiles, what are this chips are the design and what chips are being used. So CSP, chip scale packaging, are used in the mobile phones, wearables, and IoTs, as these are low profile and high density performance based. Then SIP, system in packaging. So yes, it combines multiple dies, logic, and memory in one package itself. So it is used in advanced level packaging like smartphones. Then actually, basically, what it is used like, because it reduces the board space. So yes, we are using this in this specifically smartphones. Then MCM, multi-chip module. Basically, there are two or more dies integrated into one module. So each die may perform different function. Individually, die will perform individual performs, and it is basically used in aerospace, like aerospace, because there we are supposed for the high computing performance. So yes, we are using MCM, and there are additional few more as you can see in these images, but these are not like we are not using, that's maybe used for the research purpose, but we are not using into our daily life purpose. So yes, these are the basic which we use into our day-to-day life, from using a cell phone to our like a TV and everything. We are using this kind of packaging, mostly used packaging. Now we will see how is in wafer is being sliced off, which is a dice, and then a wafer sawing methods. Okay, so wafer sawing methods, like firstly we are saying that there are different methods how we can individually remove a die to form the wave to form a device to form a die. So yes, firstly we are going to see about blade dicing. So there is a diamond cutter, as you can see in this images also. The saw which is being displayed in this image is having a diamond mounted on the outskirts, and then it is going to cut the wafer. There are markings on the wafer, and with the help of that marking, we are able to saw that we are going to saw that individual die. So the pros and cons we will also discuss why this method is better, and then we will decide like which method is being used for which purpose. So yes, this is cost effective and high throughput. The cons of this blade dicing is like it causing chipping and mechanical stress, as we can understand from this images also, like because the chip will get mechanical stress because of the diamond cutters and it will be getting damaged, and it is not actually suitable for ultra thin wafers, and it will damage the wafer completely, and the whole process which we have fabricated would be just losing its yield performance also. Then we are going for the laser dicing. So, what is the laser dicing? So, that is like consider of a torch and a light putting onto your hand. So, we are just putting this laser on our hand so that we can see that we will getting heat. Even our hands will also will like for a few seconds after we will thinking that it's a burning kind of sensation. So, yes, same as laser dicing, we are going to use this focused high laser beam, kind of UV or IR radiations. So then we are going to put that laser onto the wafer, and then we are going to individually tie the wafer, and then we are going to get a single device. So yes, firstly we will discuss again the pros. It's like contactless. So yes, we are not eventually using or damaging, or most important is like there is no uses of our hands. So contactless, brittle, it is ideal for brittle wafers, and then clean cuts with minimal I mean with minimal problems, like it's easy to remove it. And then the cones, yes, it can introduce thermal damage, not properly, but yes, it can be controlled. But yes, it's a kind of cones. Then yes, obviously, as this laser is already an expensive equipment, so this is very costly, cost effective, and we cannot use like into the research purpose every time. It's okay, but to use for the one or two types of research purpose, but not on a regular basis. And then plasma dicing. So as we saw into the sputtering also, we were generating this plasma, and then plasma was getting to the wafer to deposit. Same as this, there are the markings, and we are going to generate the plasma. Then this plasma is going to on this marking, we are able to the die individually cut the wafer into the dies. So again, the pros and cons. So in this plasma, no mechanical or thermal damage, then clean edges and best for the ultra thin films, basically. And like cones is like it's complex process, because to generate the plasma, it's again the a long process, and eventually it's higher cost, as this plasma generation is also having a, like we can say it as it's complex and bit of having more complex structure. So yes, we are it's higher in cost. Then scribbing and breaking. So think of a paper and like paper, and then when we have to cut that paper, we are just putting our nails on the scribbing, and then after few minutes we are just tearing out the paper. So yes, a same kind of this is scribbing and breaking. There are markings, there we are providing the mechanical scratches over on the wafer surface, and then breaking it manually, or either providing the stress. It was basically used in the older days and low value application. It's not basically eventually practiced by now, and like is the main disadvantage of using this was low precision, and it was actually breaking the devices also. So not practiced, I mean it's not eventually safe to use also. Then silk dicing, it's a kind of again a laser dicing. Here we are using the focused laser beam inside the wafer and creating the subsurface inside the layer itself, and then the die are separating by applying the stress. So the pros against for this are no surface damage, and then it's ideal for MEMS and sensors. And the cones is it's like expensive equipment, as this laser was also laser dicing was expensive. Again, this laser using synthetic dicing was is also expensive. Then the last one is mechanical sawing. Think of it like mechanical instruments and cutting the wafer individually. This is just, for a single die, you can just remove the from the outskirt of the wafer. You can just remove the single die. It's not actually you practiced over this, but yes, if in case we are already knowing this die is already damaged, and we want to remove the single die from its edges of the surface from the wafer. So yes, we are going for the mechanical sawing. And then after like wafer sewing, I think we have cleared what is wafer sewing, and now we are going for this. What is the die attach process? As we got to know, like what is a die? Now, a die is actually being attached on the surface, which is the substrate. So now, from now onwards, I will be using the word substrate as the base layer, and the die of like which we have created the device. Okay, so it would be more easier to understand also. So firstly, we will understand what's this in the image. So basically, why we are going to do this die attach process. So actually, the individual die are being diced and then physically and thermally bonded as a package to the substrate, preparing them for the electrical connections. This is the main reason why we are going for the die attach. And then the process, in this you can see that we are picking up the die, and then onto the substrate we are going to stick it. That's the lead frame. And then curing, like we are going to modify it, like solidify it. Okay, so this picking up the die and then attaching it, and then pressing it over the mechanical or any of the thing, and then curing it so that the die gets stick onto the surface. Think of a gum and a paper, and a stone. We are stitching the stone on the paper. Same is that. Okay, so there are types. There are two types of the materials. Basically, we can think of epoxy and polymer. Basically, this both materials are adhesives. The gum, which I said, into the paper and a stone. Okay, the same is the die attach epoxy. Okay, epoxy and polymer. So we will understand what is a epoxy polymer and epoxy and polymer with this characteristics, advantages, and limitations. So firstly, we will go with the epoxy adhesive. Basically, it's a thermosetting polymer that cures under heat. Basically, we are going to provide heat, and then it's basically available in one part pre-mixed or two parts like reasoning and then hardening again and again. Advantage: firstly, it's low cost, widely available, then good for mechanical bonding and works for low to medium power applications. Limitation: it's like in this thermal conductivity is not preferable. I mean, as this comparison in terms of polymer, it's like preferring low, and then it may get crackled under extreme and thermal cycling, and it's basically sensitive to the moisture eventually, sometimes of the some formulations also. So basically, where it is being used, most common applications which are the like memory, IC, then microcontrollers, then standard logic chips. Basically, it's used in there. Then polyimide adhesive. Basically, what is polyimide? So its characteristics are its high temperature, chemically stable polymer, and then applied over the thin films. Yes, thin films or the paste. In that way, it's basically excellent for the electrical insulators, and it's basically the flexible device. Flexibility is much more preferred over here. So advantages is like it's high thermal stable compared to the epoxy, where which we said like it's not prioritized. Here it's prioritized. Then excellent chemical resistance, long term reliability, eventually into the harsh environment also. Then limitations, it's yes, obviously if this if any of the product is having all the advantages, then there must be any of the limitations. So first limitation is it's a higher cost, and then more difficult to process than epoxy. As this is a complex structure, we have to eventually go to the difficulty levels also. So the common application which we are going to use for the polymide are like the aerospace device, like an ICs used in the aerospace, then automotive ECUs, high temperature sensors. So yes, these are the main two adhesives which we are going to able to use for attaching a die to the substrate. And then after using this after creating the die attached layer, we are then going for the like wire bonding or the flip chip. Like what's wire bonding and flip chip? Okay, so what is wire bonding and what is flip chip? The think of it. There is a now it's being stick over the a die is being stick over the substrate. Okay, then how to make the connections? So yes, we are going to make the connection for electrical and thermal connections basically firstly, and how we are going to connect. So from that concept, think of a wire bonding. There is a wire which is being connected on the die and to the substrate, and then we are going to use it same as a flip chip. So there is a die which is being flipped and onto the substrate pasted. Okay, there are two methods we are going for individually one of the steps. So basically, firstly we will go for this wire bonding, and let's see what's wire bonding. Okay, in this image there are four images A, B, C, D. Okay, so think first of A image. There are the wires. Okay, there is a substrate and there is a die and the substrate. In between the connection is done with the wires, and then wires could be of gold, aluminum, copper, or silver. Depending upon our requirements, we are going to change the uh, material of the wires. Okay, so what is in this, you can see in this B image. If you want, I can zoom it. So in this, as you can see, there is a sub lead frame and there is a die. Okay, so firstly the first bond is being created on the die, and then second bond, which is called eventually called as stitch bond, it is connect on the lead frame. So that bond is then retraced, and then we are getting the complete wire bonding structure. Okay, so as you can see into the C image also, there is a substrate and the die, and the wire bond is being done, and track. There is a track where it is being fitted. I mean, this is the bond, and there is again a bond. Okay, you can see in this D image exactly the bond pad, the die, the ball bond, the fine wire, and the bond wire. Okay, lead frame also. You can see everything clearly. This is a wire bonding techniques. There are three types of wire bonding techniques: thermosonic bonding, ultrasonic bonding, and thermocompressing bonding. Firstly, we will go with the thermosonic bonding. Actually, it is basically common for the gold wires. We are using for the gold wires. It combines the ultrasonic energy around along with the heat and the pressure, and then it's actually low bonding force avoiding chip damage. Then ultrasonic bonding. So basically, what is ultrasonic bonding? It's basically used when we are going for the aluminum wires. We are going for the ultrasonic bonding. In this, no heat is being required, and it's completely rely on the ultrasonic scrubbing. Okay, like there is a think of a wafer is being into the uh, a lunchbox. Think of a lunchbox, and there is something into it, and we are just shaking the lunchbox. Same kind of, it's ultrasonic bonding. Okay, then thermocompressive bonding. Thermocompressing bonding is basically using heat, temperature, heat pressure, and with the ultrasonic energy. It's using everything, and it is using older and specialized packaging. This is the complete wire bonding, and the application where we are going to use this wire bonding is low to moderate input output devices. Then analog ICs, memory chips, and sensor. Basically, consumers electronics and automobiles, and eventually industrial packaging also. So yes, the disadvantages of wire bonding are long wires. Long wires will produces signal delay, and not suitable for high frequency, because this will disturb the frequency range also. Even the die area is larger due to bond padding and the spacing which being created. And this eventually we will the large number of if there is a circuit is having multiple numbers of input outputs, then this will create a mess. So to avoid this mess, we are going to use this flip chip technology. uh, let's learn about what is flip chip technology. Moving to the next slide. So, what is flip chip technology? In this image, also, you can just imagine the image and think on a way, and you will be getting it. So firstly, we understand what is flip chip technology. So flip chip technology is an interconnecting method where a die is flipped down and then connected directly to the substrate or the package using like solder bumps placed onto the die that with the input output pads. Okay, this will eliminates the need of the wire bonding, and then it's like shorter in signal path, better in performance. So yes, we are using this flip chip technology. So what is flip chip? We will understand in this way, like the advantage and limitation. Firstly, it's having shorter interconnections, then higher input output density, improved thermal conductivity, and enables smarter and thinner packaging. Yes. In this image, B image. Okay. First, there is A image, and there is the second one is the B image. In B image, you can see there is a semiconductor chip, which is a die. It's being solder bumps are being provided, and then after the solder balls are being created, we are flipping the chip, and there is a substrate over here, and then over the substrate we are going to attach that die over it. So there is already created there is on the surface there are all the solder bumps, and again we are going to provide this flipped chip, so that will create a structure which already compact here. Okay, there is no wire connections, there is it's like free from the wire, and there is no mess eventually. So again, if any of the technology is having pros, it will definitely have the cons over it. So the limitations is, yes, it's more expensive process, and the equipments are also to create this technology. I mean, to create this process also, this is the equipments are expensive. Then precision alignment. As I said, there are the solder bumps on both the ends, on the surface level also, on the package also. So there is the alignment. It's also required to be precise. Then there is need of underfill, so that to handle the stress, preventing the cracker, so that we are later then we are going to provide the underfill material, the same as we used for the die attached material. The same material we are going to understand in the encapsulation also. In that, I will make you understand clearly how is this underfill required and used like to handle the stress and prevent crackling. Then for it's no cost effective for low pin count devices, and the application which we have used for this flip chip technology are processors like GPU, CPUs, and then RF and high speed communication ICs, and then high performance FPGA, eventually camera modules and sensors also. We use the flip chip technology. After the flip chip, the device is being flipped, we are going for the encapsulation process. So basically, what is the encapsulation process? Uh, okay, we will I will answer all this sorry questions into the last question answer session. Firstly, we will just go with this.
Yes, firstly we'll go with the presentation and last 10 minutes we'll flash the questions.
Definitely, sure. So there is a one video which I'm going to show for this encapsulation process. As this in this video, you can see in that way the die is being already I mean connected onto the substrate, and then we are going to protect it from the surrounding layer. Encapsulation. We are going
Actually,
to
the video is not like supporting this website, so it, it is just not
okay.
supporting the website.
Okay, no worries. I will just explain in this image itself, and then I will attach with this into the YouTube. I will just attach with this providing the link. Okay, I can share with the middle.
Yes, surely I will append that. uh,
Okay.
yeah.
Okay, okay, no worries. So in this image, basically, firstly, we will understand what is encapsulation. Basically, it's the process of covering the die and the interconnect using the materials like epoxy, resins, molding compounds, and or eventually coating, depending upon the package type. So basically, what does it does? It prevents from the oxidation and corrosion. And then to enhance the mechanical stress and eventually to improve the thermal cycling tolerance. Why we are needed for this encapsulation is because this die chip and its connection are very delicate. Okay, so this wire bonding flip chips are being exposed into the environment to to make sure that this doesn't get harm or any of the crackers or it's like short connections, electromigration, corrosions, mechanical stress failures, so that we are going to use the encapsulation process. So there are three materials, as 3 to 4 materials. After this, we are going to understand what are the different types of encapsulation. Okay. So firstly, we will go for this globe top encapsulation. Think of it, there is providing a fencing layer over the garden. Okay. So there is a fencing layer, same as this globe top. There is a fencing layer over the device or the package, and then we are adding the raisins over it. Okay, this is a technique. So the and then solidifying, definitely we are supposed to do the solidifying here. Okay, so after solidifying it, making sure that this encapsulated layer is being actually I mean we can more see that it's being not exposed, the die and the chip is not exposed. Okay, the completely chip is separated from the environment and we can use wherever we want. Okay, and then in this globe top there are pros and cons also. So basically it's excellent for the mechanical protection, good moisture resistance, and it's widely used for this wire bonded packaging like FDP and DIP, as we understand in understood from the types of packaging. Okay, so limitation is like it's not suitable for the open dies where individuals inspection is needed. Then we will go with the conformal coating. In the second image, there is a conformal coating. So what is basically conformal coating? So think of a PCB, then we are providing a layer over it. A layer is of a conformal coating, a thin liquid coating, especially of silicon and then poly acrylic, or sprayed over with the brush over the die and the interconnects. Basically, it is used when the components are mounted directly onto the PCB, like chip on board, COB. Okay. Again, we are having pros and cons. Like pros is maintaining die visibility, flexibility, lightweight, and can be selectively applied. And the limitation is like less physical protection and then suspension to wear in aberrations. Basically, it's commonly used in lead LED packages, okay, and then low profile devices. And then in the third image, you can see it is a flip chip underfill. Okay. As I said into the flip chip also. Now here we will understand. In this image, there are three sub parts. Okay. Firstly, we will see of the A portion. Okay. So there is a chip, there is balls, solder balls, and surface. And then in third image, third part, we can see that there is underfill material, and then providing the heat that's being purified and we get the complete uh, package. I mean, we get the complete connection between the die and the surface. Okay, so then this is the first part, and the second part one is the B. Okay, in this B, firstly there are the bond pads. We are going to put the underfill material, and then the flip chip is being attached onto the surface substrate. Okay, and then providing the heat. Okay, it's three step process. The last one is actually a complex process. In this, you can see that there is a created mold. Okay, so this mold will be providing, and then after providing the mold, we are going to inject the underfill material, and then we are going to provide the heat to purify it. Okay, so this is a bit complex process and eventually expensive process, because for the individual die we have to create the individual molds, and that's not preferable. Okay, so these are the three types of underfills or encapsulations which we are going to use to encapsulate a chip. The pros and cons of this flip chip is also like limit. Pros is like it's basically absorb mechanical stress. We get the perfect encapsulated device, flip chip device. Eventually prevent solder joint crackling also, and then improves heat conduction. Sorry. The limitations of this flip chip is like it's yes, costly, process timing, and require precise control flow. Eventually, it's used in high-end SoCs and mobile processors. Just we can use this glue top encapsulation and conformant coating. Now, after what we can say encapsulation, we are going for this plating, or we are going for the laser marking. Okay. From now, Bhavesh would help you with this laser marking, make you understand. Okay. Thank you.
So laser marking, basically, we understand why laser marking is to print or do some sort of a uh, print on the device or sort of a plastic material, because package is a plastic or a polymer material, so we need to make some sort of print. Now what we are gonna print on it? So it could be generally your the company's name, code, a name code of something, because generally we have an Aadhaar card to identify ourselves as an Indian citizen. So based on that, even to detect or trace or know whether what sort of package is that, so we need to understand, we need to have some sort of an identification for that package. So we do the laser marking. Now laser marking can be name of the can be naming, can be a QR code, can be a barcode, can be a serial number to identify what is it, then trace it. If some sort of ICs or a bunch of ICs is some like lost and during the traveling or a packagement while exporting it to somewhere, so it is very easy for we to understand where that package is gone. So this is a very helpful to for the tracing and identification. Now how do we do the laser marking? So there are three types of laser marking: annealing, ablation, engraving, foaming. Four types of laser marking: annealing, ablation, engraving, foaming. Now annealing, basic understanding of annealing is to heat something and to make sure heat something, and then do like focus a laser on that material such that while heating it the bubbles will form, and you will just remove that bubble part and make a proper text out of it. And during the ablation, laser ablation, as we have seen that stealth dicing, so it is almost same as the laser ablation. It will remove the top layer of the top layer of the package, because it's a plastic, so it would be easy for to focus the laser, and then we'll remove that part. And even text engraving, it is similar to laser ablation, but we'll just focus the very high beam laser, and then we'll make some sort of print, and it would be kind of a black only, because laser doesn't change the color. So based on that, it will very high focus. It has its cons that it might damage a material inside, or if we do it very high focus beam, so the engraving can be a problem. Then foaming is just to make sure that we do some sort of a chemical composition, like we focus a laser on the that material package, and then that high focus laser will make do the chemical reaction and color change the color of the text such that it forms a proper identification of that material. Now plating, the best understanding for the plating is to make some sort of a layer or a bond pads to connect it with any other another IC, or basically it is for the wire bonding and for a better connectivity. As we can understand, it can be a metallization part also. So it is generally done at a for the lead frame, ball grid array. You can see it on a QFN package, quad flat no grid packages. So it is generally for the metallization of the part, where we can make some metal layers and then connect it with the other material, other wafers or the other die pads, not the wafer, other die pads. And generally it is used at wire bonding. And for this wire bonding, and these are connected at a memory level. We see the 3D IC packaging, 2.5D IC packaging, even right now 4D packaging is being done. So generally we make SOCs and then joint it one upon one to make a whole building, like a stacking on it. So this plating can be very easy to make a small package, but in everything is integrated in a one package. And with that, plating is very much helpful to make a proper conductive layer. And even it is as a conductive layer, it should be a corrosion less corrosive, or need to be preventive from the corrosion layer. So plating is generally done for a better connection. As you can see in this first image, we do the electrolysis plating. Like we generally do the chemical reaction, either do the CVD is generally chemical vapor deposition. We do the thin layer of a metal, and then we do the redistribution layer. We form a small pads on it, and then smooth it, like do the CMP, chemical mechanical polish it, to make a uniform layer, to form those bond pads to connect the wire bonds. Now if you see, there is an image of a proper like UBM, under bump metallization. It is generally a silicon is there, then there is a passivation layer. Passivation layer can be an oxide layer or a nitride layer, whichever we want. Then we have done a lithography. So based on that, a photoresist layer is there. And then we grow a copper layer on it through any metallization process. And then we do a antimonide, antimonide silver electroplating. Then we remove it. Then we remove the photoresist layer. So we have a proper metallization part, which can be helpful in a BGA, ball grid array, wire bonding, to make a proper under bump for a better metallization specifically. And third image is same as to do the metallization of different dyes, to make a stacking of it, and then for a better electric conductivity and a thermal conductivity also. Now singulation, the basic idea of a singulation, it is almost similar to the dicing, but a singulation is generally at a wafer level, package level, not at wafer level. At wafer level, we do the dicing, and we take a die, then we make a package out of it. At a singulation, we have a package, and while we do the packaging, we need to make sure that remove the package with the blade dicing, blade or a mechanical blade sawing or a mechanical sawing. Then this could be a whole process. Like I'll make you understand with this flow. Wafer is come from a quality check, then we do a proper lamination, or you can say taping on it. We do a back grinding of it. Back grinding because to have a less power dissipation, because we need to also make sure, while all these processes been done, if our die is very thick, so power dissipation can be a problem, leakage current can be a problem. So also we need to make sure that there's wafer this polishing also has to be done. And then after that, we remove that lamination part, and from this de-taping, which is then we do this singulation, like saw it with a mechanical saw, and then we do the inspection of that specific package. So this is how we can do the singulation. I'll just add one thing. If someone wants to understand what is dicing, so it is just a single statement. Dicing can be a singulation, but a singulation cannot be a dicing. It is a very easy statement for anyone to understand. It is, I'll show you with this. You are dicing a whole wafer and taking out a single die. But even at as Jaishri said in few minutes back, that there can be a damaged die or a improper die which is not meeting our expectation up to a parametric level, which a company wants at, which we want at an industry level. So we can singulate it, and then we can remove it, and then do our other further processes. So it is basically dicing can be a singulation, but a singulation cannot be a dicing. So it is a general idea. Dicing can be at a wafer level also and a package level also, but singulation is generally at a package level. So this was a singulation and dicing. Now testing. Now generally, even if we try to make some product, we need to test different things. It can be a functional test, it can be a parametric test, but also need to make sure it is perfect with the environment. We need to do different sort of testing. So these testing are very important at a specific stage. So while doing this die attach, wire bonding, the flip chip processes, simulations, we need to understand, are whatever this process we have done, are they matching our parameters what we want exactly? Because if we make something, a product or a device, we have a proper sort of parameters have given, so we need to maintain those parameters. So based on that, we have to make those things. If we have given some sort of a device, so we need some sort of 2 into 2 die. So we need to understand what are the things we should be considering, and based on that we need to make a die from a design side, then it would be go from the fabrication side. So testing has to be done properly. So there are two types of testing. First, at a wafer level testing, and then there is a package level testing. Now wafer level testing can be used, it is a simply, we have got a wafer. It can be, those are probes are generally a small pencil kind of thing. You will attach it like this, and then pass a current and a voltage through it to understand what are the electrical parameters, and based on that we can measure what is the threshold voltage, leakage current, vds, vth, everything. So it can on a very if you see the third image, it is a probe card in which we put our package on it or a wafer on it, and with that it could do the parametric testing, functional testing, and based on that we'll get a result. We'll just have to add those parameters inside those probe card, and we'll get different parameters which we want. And at a very first you can see this is kind of a uh, like curve tracer. So based on that we can understand what are the IVCV curves we are getting, and we can test it at an electrical level. We can also do the burn-in self-test. So there are different testing we can do. Now at a package level testing, uh, package level testing at a electrical testing. Generally at electrical testing, these are probe tester. As I said, electrical testing can be a wafer level and a package level both. So at a, if we get a package level, so we can turn it with the probe. We do that pencil kind of thing, turn the voltage and current, and try to understand what is electrical testing. We check the parameters, how they are going to be uh, at a functional these functionalities are followed. If I have made a digital circuit, whether it is continuously showing the 0101 bits kind of thing, what are the timing equivalency, even a power dissipation is a very important to maintain. So while doing all these things, we need to test it at every single level, because making a package is kind of not easy. But if we say, even after making a package, we need to understand what are the problems we have faced, or so make sure to, if we do next time the packaging, these problems should be prevented while doing those processes. Now even these are kind of benchtop tester. CROs are there, then curve tracers, ACDC testing. So we need to understand how the AC and DC parameters are to be maintained. So electrical testing is very important in that, in those parameters. Then thermal testing. Now we use IC in our daily life. In ICs are in our phones, in our laptops, even in our vehicles, to have a proper automations in our fridge, everything. But we need to do the thermal testing. Thermal testing is because if we take our car to Kashmir, so it has a very cold weather. So based on that, might be a 0 degree, -1, -2, but IC should be able to work at a -40 degrees Celsius, also -50 degrees Celsius, such that it should remain at a different temperature variations. Even at a 150 degrees Celsius, it must be working at a 110 degrees Celsius. It's a very huge temperature, but we need to understand that even at a very high temperature, our IC should work at some sort of temperature range, and at that temperature range, epoxies and polymides come into the action and make sure the thermal conductivity is stable, and that, and even electrical parameters are very much uh, constant in during this thermal changes. So these are the thermal chambers where we can give the thermal shock, and thermal cycling is given such that these thermal parameters to be controlled. Now, if you see this, thermal shock is given, liquid cooling is provided. Then with those liquid cooling, how the temperature is maintained, and with those in chip cooling, and these parameters at the thermal cycling should be at between -40 degrees Celsius to a 150 degrees Celsius. In this temperature range, whether our IC is maintaining those thermal parameters or not. Now, the mechanical testing, we made an IC, so we need to make sure it should be a very much it has mechanical strength. So this mechanical strength would be followed with the encapsulation and a die attach. Because if our die would slip through the inside the package, or the wire bonds are not proper, so based on that, we need to do this thermal testing. So tensile testing strength. Now, tensile strength is, I have this package in between here. Yeah, I have this package. I'll pull it through like this. So this is generally a tensile strength test, tensile testing. Now, wire bond. We have done a wire bond. We'll melt the wire and then form a proper package on it, and then we'll test whether it's electrically connected or not, and we'll pull it like it doesn't come out, because during this mechanical it would be transported to some places. So we need to also pull it to check whether it is perfectly maintained or not, or it has a proper bond or not. Then stress and strain. I have made those ball grids inside at BGA ball grid array, the small balls while the soldering. So I'll push the stress it like this, and if the ball dislocate, so for that we need to understand the stress and strain. We need to maintain the some pressure. So based on that, these testings are very important at a mechanical level. Now, environmental testing. While sending our package to some place, there can be a different problems we see. While first of all, the while new device came in, so it works properly. For after few months or after few days, it can be a problem to maintain the package or an IC. So we need to understand how to test it properly. So salt spray testing. Salt spray testing is nothing but the corrosion test. We need, while we do the salt spray testing around the lead frames or the at the wire bond, so how much time it would take to degrade that package, or degrade that whole IC inside it. So salt spray testing is very much important at that level. Humidity tester. So even a package should work at a very humid temperature, humid environment. So humidity is the gas flow is in there, and based on that, it doesn't affect the package at those level. Then pressure cooker machine. Pressure cooker is just nothing, just uh, steam doesn't get in. our package should be like that. It should be waterproof, it should be humidity proof. Waterproof because even at a even our phone gets in the water, and we have the IP64 and some sort of parameters in which the mobile can be workable at 30 minutes or 40 minutes. The water cannot get in. So pressure cooker testing also come in this IC64 and all this, to prevent it from getting the water inside, or a vapor inside, or even small sort of a pressure inside, which can damage a wafer. And all these small parameters are very much important while doing the testing. Now, X-ray and imaging testing. X-ray and imaging testing is like, we do the thermal shock, we do this thermal testing, at which there can be a bigger chance of forming those bubbles inside it, because epoxies and polymers are kind of a polymer. It doesn't have very much high melting point or a boiling point, so it can form a bubble inside it. So even a wire bond can be like dislocated, or it can be a broken from the inside. There can be voids. So without breaking the package, we can check it from the X-ray. X-ray diffraction machine, SAM machine, X-ray photoelectron spectroscopy, to see inside what inside the package, that what are the problems inside it through a visual aspects, and need to understand what can we do different to prevent it. And there are small parameters which are to be understood in this. The small atom, even a contamination at a very small hydrogen can get inside this polymer level, so it can affect the whole package. So we need to do all the inspection at the end. So these are small things which can make a huge problem. So for that, we can do the UV X-ray inspection. Now, AT is, we can say, all rounder. It is a best form of thing. It is an all rounder. These machines are generally given at how would I say, AT is generally a machine all rounder. Inside, if we do one process and then we have to do the testing, so this machine can do all sort of testing: environmental testing, thermal testing, electrical testing, and mechanical testing. So all this testing can be done by a single machine. So this machine is generally in every ASM, core technologies, even Micron use it. So these machines are used in for every sort of testing. So if you are making a huge packaging company, you have this machine. It is very, it is huge machine, but all these testing parameters are done in a single machine. So it is very beneficial for all these sort of testing parameters. You don't need many equipments to make handle it and maintain it. You just need a one machine, and based on that you can do several testings, and need a maintenance, but it is not huge maintenance to do it every week or month. So uh, this is kind of an all-rounder. You can do every single testing in a single machine. Now, a benchtop tester. At a very small level, we need to understand electrical test or a parametric test, even a thermal test. We use benchtop tester. We have seen the CROs and every cathode oscilloscope, curve tracer, AC tester, IDQQ tester, built-in self test for ATPG test pattern generation. So these benchtop testers comes in. Even right now, these X-ray and inspection machines like SEM and tabs, these are tabletop machine. Like, they comes in a very small size. So these are benchtop testers are very small, easy to use, uh, very low maintenance, and very like not much expensive. So these are the machines which can be used for the small parameter testing and functional testing. So based on that, just to make a small package, we do go through a lot of testings, and these testing are very much important, because based on this testing we can just predict how much life cycle is there in this package. Because we now generally see that's the, that's a rough rough idea that silicon has a life cycle of 25 years. But after all this packaging, and generally we see the Japanese machine and German machines, these work for 40 years, 50 years, 6 years. So behind that, these all packages are very much useful to maintain those life cycle parameters. So we need to do this testing. So make sure that after doing another bunch of packages, this can be a very huge can bring a huge change by just changing one parameter. So testing is a very important, and it should be done one after one step. If I've done dia test, then do the inspection. If I've done the wire bond, electrical testing, mechanical testing, encapsulation, I have packed the IC, I can do the mechanical testing. So all these parameters are very important to check, and then we send it the bunch to the other customers. So I think that was it. Yeah.
Yes, I think Bhavesh and Jayashree, you presented well today, and the turnaround time today was covered excellent way. So your turnaround time while you practiced is very good. I appreciate your effort. And now I will flash one question that came. And sorry for my uh, mousing around. I was checking the message and accidentally it came out, and that might have disturbed you. Sorry for that. And Varun, I'll show your question come comment here. And the thing that I would like to say that first of all, thank you for asking because the curiosity is the key to learning. If you are curious, you are not only you are learning. When you are sharing this with Bhavesh, Jayashree, and me, every one of us and the viewer, they are also learning. So the question is, in the wire bonding, long wires lead to huge inductance. Do designers have the capability to simulate the package to understand performance and difference between wire bonding and flip chip?
Okay, I'll answer it. Jason, do you want to? Okay. So generally, wire bonding is majorly used for the memory devices, as far as I know. Memory devices, because we need to do the stacking, and then bond pads we need to take out a single wire and then connect to the other bond pads, or some sort of bonds we have to make. So wire bonding is very much useful in that ways. But at a flip chip level, we can do the 3D stacking. So everything is replacing at its own level. So even like some it is a best way to understand, to remove a huge inductance. I take a big IC at a middle, and then connect it through other bond pads. And even for the stacking, I'll stack a small one by one, and then take it bond. So even the bonds are very smaller, these wires are very smaller, the inductance could will be less compared to the these all this different huge wire bonding stacking. And also the material comes in. If you use gold wires, so it would be better for the life cycle also, and at a inductance level, resistance level. So these materials also help. And even just a design side in that, okay, uh, we need to make sure this different bond pads has to be at a similar area of packaging.
Okay, so one thing I would like to share as
Just a second. Okay. Just a second. I would like to add one example. That's daily life example. Think of while driving a vehicle, you're wearing a Bluetooth or wearing a wired cables earplugs. Okay, so you can differentiate where the wired one will be creating a noise, and you won't be able to while driving it won't be feasible for you also. So the same way, that's a flip chip and that's a wire bonding. The way you are able to decide it the same way, there are multiple you can say like pros and cons for which to use where, and the difference is being created over there itself.
So I would like to add one thing here, giving the three names. Let me flash it on screen. So these are the EDA tools that are used for this kind of analysis. In case Varun is working on the domain, you can explore in case you have some of the vendor in your site. So I think that you can do if you want to do such analysis at your end, whether you have any of these vendors at your site, so that you can explore with them. It's a very good exploring question, because first of all, when we cross, technology is something, it has no boundaries. Whenever we have our technical journey, right? So it's good always to cross the boundary and jump over the fence technically. Okay, don't do at your neighbor's house, not suggested physically doing that, so your neighbor can run after you. But in technology you should do it every now and then. You should cross the boundary, jump over the fence, and try to know what is beyond that fence. Okay, so that is highly encouraged, and Varun question is very, I appreciate. And all of us, I was doing a research in between about this kind of analysis, and different things are analyzed by different tools. So we have like ANSYS, they have a kind of physics, multi-physics simulation. I think
Yes.
COMSOL also has some multi-physics simulations. COMSOL is another company. So
Console
there
for
are,
the good.
yeah. So these are multiple companies, they approach different thing from different ends. So that's why all the EDA tools and companies, they exist, because uh, one company cannot give all the solutions, because these are highly specialized field. And even with the specialized field, if we go down under the microscope, we have further uh, precision which we need as a production output. So the production output, different vendors, they provide different tools for your analysis. So Varun, I think you have got something, and Varun also provided an answer. Let me flash it. Varun says, my guess is wire bonding is used for slow memories, since for fast high performance memories we would need HBM. Thanks for the answer. So any comments on that, Jayashree or Bhavish?
Yeah, it's true. For memories, it's wire bond, but generally now they are converting into the 2.5D and 3D packaging at even for the wafer level chip size packaging. So these are all like wire bonding can be used. So there are different ways to make sure the memories are even in high performance and a fast. So it can also be a like a similar way to do the packaging for memories.
Great. So we have one more question from Shivam. Let me flash it. Does the VGA package need I think buyer not, this is wire bond or not? So
And I
Ah,
think this is not VGA, it's like
it's VGA.
BGA, a
VGA, I think.
ball grid array.
Yes,
Okay.
yes.
So, like, yes, even though this ball grid array requires a wire bond, like, yeah, it's required, even though it's external connections. But like, this connections can be, like, we can think of like internally connections. So, yes, this internally connection to the PCB through solder ball, and then this internal dies could be connected with the wire bond also. So, it's not like definitely preferred, but yes, we can use it. Basically, it's used for the low and mid performance based GA. Okay.
Great, great. It's actually we are jumping off the fence and getting a lot of knowledge from different boundaries, and we are crossing the boundaries and crossing our limits. And thanks Shivam for asking the question. And I think this BGA and all these things turned into VGA because of your auto correction in the keypad. This they give a weird thing that even I find when I'm typing something in WhatsApp, the message I am sending a wish, and sometimes it could be a sorrow to the person I'm sending. So don't get upset about the spelling mistake. We know that comes as a parts and parcel of the auto correction of our tools, from the keyboards that you are typing. Okay, so let me flash it off. And there are some cheer up messages. I think I'll show them. I think Mohil says, excellent guys. And here I'll show this. Bharat Semi said, excited. I think this messages came early before the show.
Yes.
And Raju, this is Raj, right? Raj said, I think he has given some symbols and said here for Mr. Bhavesh. So people are cheering you up. It's a very good culture, and that culture should carry on, because we are encouraging here, because there are two shows that we are currently having live. One is the TSP, that is where we are bringing leaders of various sectors allied with the semiconductor technology, and we are having the webinar series along with the students and interns who are at the learning phase. So it's a very exciting journey. Even I am myself, I am very much excited when I am interacting with the students and we are interacting with the leaders. So there are a lot of things that stay hidden in the cubicle when you work, and when you are coming either in the podcast or the webinar, a lot of interaction is going on, and that's a very good culture. I am very much excited to carry this forward. And uh, and we have just a chat before the actual beaming of this live, so we'll have another session with Bhavesh and Jayasri, so you guys have to wait for that. So
Sure.
and yeah, yeah, so it is a series, and many more people are coming through the TSP and the TSW, and we are there. And one more thing, I am very much uh, excited, as well as I am very much overwhelmed that there is a learning part called peer learning, that whenever the students are there, they are learning from the peers, right? Whether they are working in an office or in the college, the peer learning, that when you learn from a peer, you learn the best. So the semiconductor webinar is there for a peer learning. Whatever you have, you share it. uh, you are flashed onto the our channel, which is now a global channel, and it is viewed from 90 countries, obviously not simultaneously, not when it is dimmed, but it is bits and pieces. As the sunlight goes around the globe, our views count. Even that is true for our blog. So we have a live analytics. We can see it at what time, what region is viewing. So we are not spreading the culture within India, but also we are spreading this culture across the world, the peer learning. And we are very much excited about these two series that are currently going, the TSP and the TSW. And today we had a second episode, exciting episode with Bhavesh and Jayashree. And myself, I was very much excited about this session. A lot more information even come to me. And we will be meeting in another episode. Let me check whether we have any more comments. I don't think we have any more comments. So another thing, I would like to appreciate you, Bhavesh and Jayasree. Your infographics that you have put in the slide were very good. Keep it up. And this was helping for someone to grasp the meaning very easily, who are even not from the domain. So we, from the questions, we can see that there are knowledge transfer happening live. And that's all, I think. Anything, Bhavesh or Jayasree, you would like to speak before we go offline?
Yeah, we just want to thank our parents and our faculties from Nirma University, Dr. Chetna Chauhan, Dr. N.M. Devasri, Dr. Ankur Pandya, Dr. Tanuj Gupta. They all helped us through all these things, and even those small problems we were facing. So, like during this week, so they helped us on all these small things, and just that's it. I hope like we learn how different all things different things from them in every possible domains. And again, thanks to them for helping us in all these things.
Yeah, we have
Eventually, they
another.
provide us a platform also, from because they were supporting us from this. Eventually, steps to get to hands-on experience. Like they were the only one to help us. Eventually, the midnight question answer sessions. Yes, our professors were very helpful. Like they supported us throughout our journey and during our master's journey. Thanks to all thanks to them also. Eventually, that's a great. I mean, professor-student relation, and we are like.
Yeah, Jayashree, last sentence got broke due to the network transmission. Can you come again about the last sentence?
Just it was just a word like this was possible because of our professors. Thank you for providing such platform eventually. Thanks to them also.
So thank my thanks go to all of them whom Jayashree and Bhavesh has shared, and I would like to flash three more comments. One is from Pinky Agarwal, and she says, "I'm proud of you, Jayashree, beta, and God bless you." And
Yes, mama, it's my mama.
great, my pranam to uh, her, and it's good that you can see her performing live in a global channel, and from our side we also uh, give blessings to Bhavesh and Jayashree that they go far ahead in their life as a senior. So I'll be flashing it off, and another comment came from Amigo. I don't know this is a name or nickname. Great work, Jayashree and Bhavesh. And he says again, or she says again, keep it up, guys. So this guy may be, or he or she may be in your network, so you might be knowing. So I think we'll conclude today's session here. It was a very crisp and enjoyable session today, and there I think there was very much network latency was there. Very less amount, not very much, very less amount of network latency was there, and all broadcast happened correctly. Sometime because of the intercontinental network through the undersea cable, sometime we have. So that is the practical thing we must consider. So without any further words, I will say bye to Bhavesh and Jayashree. Thanks for accepting the invitation and coming into the semiconductor webinar. And as promised, we will have another one. We'll take the calendar, look at the calendar, and schedule it properly so that other guests are also placed. And obviously, you have some energetic times in between so that you can great energy when you come back. So here, I think another comment came just before logging off. Let me flash it. Pratham Sharma shares great work and good information. So yeah, I think we all have come here for sharing knowledge, because the Tech Simplified TV platform is for sharing knowledge, and we have here peer learning through the webinar series, so that lot of information is shared, because all of these are industrial info, and many of them are not available maybe in books in the form and shapes and with the infographics that you see here in live. So here again, Pratham Sharma says, keep shining, Bhavesh and Jayashree. So I think and I think here Ravi Kumar Advani says, keep it up, beta, God bless you. So I think he's a senior from your family, so my pranam goes to him.
My father.
Yes. So it's very good to see that the next generation is paving their way and having success in their life. And again, from our side, from Tech Simplified TV, we encourage the youngsters to become the new leaders in upcoming decades. So that is why we are having the podcast, and we have this the live shows, so that they are projected well. Yes, thank you everyone for your overwhelming response, and thank you Jayashree and Bhavesh together that you presented a second webinar, and again we are collaborating in next couple of months. Again we will be beaming another episode, so this saga will continue. Thank you, and viewers, thank you for staying so long. Thank you very much. We appreciate your patience and eagerness to learn new things beyond your beyond boundaries and jumping off the fence, obviously not your neighbors or your house physically, in the technical fences you are jumping off. So bye for today.